Hello, and welcome to the 7th episode in this series on writing our BF.NET compiler. This time I want to look at adding some error handling to help the developer when they're writing their programs. There's 3 error cases we want to initially report. The first 2 are similar with the interpreter, where we had an uneven number of open and closing loop symbols. So for example, we could have more closing ones than opening ones, or conversely more opening than closing. The other error I want to report is when we've got an empty loop. Now this can mean one or 2 things. If your program consists of just an empty loop and nothing else, then actually this command actually does nothing at all, because the current cell in our table will contain a 0, in which case the loop will just skip through and nothing will happen. If however your program was like this, so then the tape currently contains a 1, then this loop will never terminate because the predicate or the guard will never get back down to 0. So either way it's a problem for the user, because either they've written some code that never does anything, which they probably didn't intend to do, or it's going to go into an infinite loop. So when we report errors back to the user, we need to tell them 2 things. We need to give them a description of the error, and also we want to tell them the location within the program where the error occurs, so which symbol we think is not matched. So the complication we have is we've got an optimization stage which takes our program and replaces these sort of characters with a symbol +8. This means that these symbols now appear in a different location to the original program. So we can only do our validation after the optimization has happened, but we need the original locations. So this means that when we build the tree to begin with, we also need to record some additional data. So we will start off by doing that. So that's in our parse source code. So when we create a new block, we also need to tell it its location within the application. So the first symbol in the program will be at location 1, so it's going to be 1 bound, 1 based, and each time we go around the loop, we just increase that by 1. We have a new parameter there called location, which is a read-only property. So we'll make that mandatory for a second. Maybe we won't make it mandatory. So there's 3 places we set it. So when we create the root block, that's going to be 0, that's fine. When we create the new block, we've done that case, that's fine. So the other one is in the optimizer when we're rewriting a block, in which case it's important we pick up the original location. So the original block is that one. Location. In fact, that's a bit of a bad name. Why don't we call that original? Okay, so now we know where the error occurs. So whilst we're here, we have the first case, which is if we hit a closed loop and we are matching open loop, then that's an error. And we know that's happened because we don't have a parent, because our parent will be null, because we've got nowhere to move up to in the tree. So that's null, that's a problem. And then we need to decide how we can report errors. So there are 3 possibilities, at least. One, we can throw an exception and stop parsing. Second one is we can write to the console at this point and probably stop parsing. Or we could return a list of errors. So because you could potentially report more than one error at once, so say you've got 2 closing loop terminators, we don't really want to stop parsing after finding the first error. So in fact, we want to just return a list of errors. So we need to a class to hold that error information in. Error. And that's going to have 2 bits of information. It needs its location and a description of the error. And then when we pass it, because we're already returning a block, so we should pass in a list of errors. And we know that if we get back an empty list, or if the list is still empty at the end of this, then we didn't have any errors. Errors. So now down here we can add our error. So the error is that does not have a matching. So the next case is when we've got more opening than closing. So we can only tell that once we actually get to the end of the program, which I believe is there. So at this point, if our parent is an object, that means we haven't gone back up to the top. But we could actually have multiple again. So we could say while it's an object, we've got a problem, so we can report our problem. And the problem is that does not have a matching that. And the location of this is it the location of our parent or is it our location? So what we say, we've got more opening. So if we had that, that error will be our, yeah, it's our location, isn't it? Location. And then we can just walk up the tree. So we say so we pretend, yeah, so what we're doing in effect is we're pretending we did have a closing bracket and we're doing the same action. Okay, that's those two cases. So then when we get to here, if we have any errors, then we've got a problem. So now we need to display our errors. So there's a better method to do that, I think. Errors. And we probably can just return at that point. And then to display errors, it's our pen. Nice red colour. And we loop over our errors. And for each one, we just display it to the screen. So error at position, which is our location, and then the details of our error, and then we should be good and reset our pen. Okay, so let's try breaking our program. Let's add, oh, that's quite broken. Let's add one of them in there and another one there. Position 1 doesn't have a matching. Does not, yeah, that's correct. 9-4. Yeah, interestingly, our errors are going to be reported in reverse order because which is a bit unusual, I think. Okay, and try the other case, which is we've got more closing. So let's put an extra closing there and one there. Ah, we've hit a different bug. So what's happened here? Ah, see the bomb. Yes. So we're going to when we hit a closing bracket which we're not expecting, we should just ignore it because there's nothing else we can do about it. So position 4 doesn't have a matching opening. Yes, that's correct. 108, which presumably is, yeah, it's going to be the last one. That works. The only thing we could do is when we're displaying the errors, we could order them. Right, location, so they will now appear in order. So we should get 1 then 4. That's better, I think. That makes more sense. So the next thing we want to do is detect when we've got infinite loops, such as that one. And we can do that after. Actually, we'll do that. Do we do that in the optimizer? We can either do it in the optimizer or we can have another stage. I think we should have another stage that does it. So we've optimized the code, and now we can now have a method for check for empty loops. And we need 2 things. We pass in our loop block, which we're going to check, and also our list of errors. And as before, if we have any errors, we display these afterwards. So we need some sort of recursive call here. So if I'm allowed to do it. So we look at all child loops of this one. Or let's call it loops, in fact. If our loop doesn't contain any instructions, then we've got a problem. So then we can create our new error. So should just be loop estimate. So if the loop doesn't contain instructions, then we report the error against that loop. Empty loop either will do nothing or loop infinitely. Otherwise, that loop's fine, so we can just check any child loops that loop. So we just recurse down each loop. Virus. Around. So it should be position 3. Empty loop, even will do nothing or loop infinitely. Okay. So the case we haven't catered for yet though is if our loop contains this. So this is still an infinite loop because those two should get combined together to be a modification of 0, and so at the moment we still include modifications of 0 in our tree, we just don't emit them as C#. So if we look at our emitting code, we just ignore anywhere quantity is 0. But what we actually want to do is not put it in the tree to begin with. So to show you it not working, if we run it now, I think it's just ignore that error, which it has. So our fix is in the optimizer, we only want to add these blocks if they're actually going to do something. So all in those places. Instruction. Let's just go. Instruction does something. A good name. So I think this is easy enough. If the instruction is a move instruction and its quantity is 0, then we return false because that instruction doesn't do anything. Likewise, if it's an increased cell instruction, its quantity is 0, we return false because it doesn't do anything. Any other case, and we return true. So other cases are it's got a non-zero quantity, or is any other type of command. Okay, so that's now worked. That's now correctly detected that that's an infinite loop. And just make sure we haven't broken anything else. We'll take that back out. So this time it should run without any errors. So there are some more optimization techniques we can use. For example, if we had some code that did that, so that would have the effect of setting a value in the tape down to 0. So it doesn't matter what, assuming it was a positive value to begin with, so say it was +5, then this would run -5 until it got to 0. So at the end of that loop, we know it's going to contain 0 in that position. So we could optimize that loop if we added a new command, for example, to be equals 0. So instead of having or as well as having a move and an increased cell command, we could have a set cell to 0 command. So that would be one optimization. So then we wouldn't have to run the loop. You could always set it to 0. But I think we're going to leave that type of optimization for later, because there's also other things we could do, such as if you had plus move left plus move right plus, then these two pluses are actually updated in the same cell, and there's actually a +2. And I think we can actually detect that type of thing by just reordering the commands. But that will be a job for another video. I want to move on to actually generating the IOut in the next video, or certainly start looking at doing that. So I think we will leave the optimization stage for the moment. Thank you for watching.